Welcome again to another lecture. Here we're going to go over some more with Newton's laws and applying them. To recap from last time, we talked about friction and how to quantify that, and we made a distinction between two different types of friction, both kinetic friction and static friction. And we explored an example that included kinetic friction. We're now going to explore an example where we look at static friction, and we're also going to include two dimensions in this example, whereas we were only really looking in one dimension when it came to the Atwood machine. Okay, so this situation that's specified here involves gravity, tension, friction, the normal force, basically everything we've discussed so far. So the scenario is that you have a truck which is towing a car, and you want to know what kind of tension will be on this rope here, and whether or not a certain cord that you're going to try and buy will be able to withstand that kind of a tension. Okay, the given information is not terribly much here, but it is sufficient to solve our problem. First of all, we know the mass of the truck, and we know the static friction coefficient, which is listed here. Notice that this mu value does not have a unit. That is on purpose. If you recall that the frictional force is going to be proportional to the normal force, and that this is just a constant of proportionality, the coefficient of friction. And so we've already gotten newtons here from the normal force. We don't need a unit here, so this is a unitless quantity. All right, and what we want is to be able to travel at a constant speed with this truck. Okay, so the first thing we're going to do is try and figure out what our free body diagram should look like. So go ahead and take a look at some of these possibilities, and as usual, if you would like to pause the video and think about which one you think is correct, and then when you come back, let's talk about trying to deduce what we can throw out as not correct here, and then we'll be able to get to the correct answer. So first and foremost, the weight force is always going to be pointing straight down, right? So we can eliminate choice C from the possibilities here because it's obviously not going to point off at some weird angle like this. The next question is, what should the normal force be doing? Remember that the normal force should be acting perpendicular to whatever surface where the object is in contact with. And so these normal forces which point straight up are not perpendicular to the surface, because the surface would have to be horizontal in order to be perpendicular to that direction, vertical. So we can eliminate these as well. That leaves us with choice D and choice E. Might be a little bit tricky to ascertain what we want here, but we can do one of two things. So choice D and choice E both have the right kind of property for the normal force, where we have the direction of the slope going something like this, and you can see that in both cases the normal force does make a right angle with that surface. So that's all well and good, but now what about the friction force and the tension force in this direction here along the slope? So one way you can try and think about which of these two is correct is to go back to the problem statement for just a second, where it said that we are moving at a constant speed. So we know that whichever free body diagram we choose should result in effectively no net force in any direction. If we're moving at a constant speed, then we want these things to effectively cancel. So if you look at this choice E, you can probably deduce here that there's going to be some sort of net force off in this direction down the slope. So that can't be the case. Otherwise, we would not be moving at a constant speed. That means that the only correct choice can be choice D. Okay, so how can I think about this friction force? Why is it pointing up like this, up the slope? So the action of the wheels pushing against the surface. So let me draw a wheel here. They're going to point this direction, push this direction onto the surface, so then the surface is going to push this direction back by Newton's third law. I go into this a little bit more in detail, by the way, in the worked example of the truck towing a car, which is a separate video on the playlist. So you can go ahead and take a look at that if you need to wrap your mind around it a little bit longer. But there we have it. Choice D is the free body diagram that we like and that we want. So we want to move forward then and try and figure out what kind of tension is going to be on this cord. So we start with our free body diagram, and notice that I've done something a little bit maybe not what you're used to. If you go back to the steps to the problem solving process that we had done very carefully and very much in detail in Unit 1, remember that step 1, so I've implicitly been following those same steps now, I'm just not labeling them as such, but step number 1 that we had enumerated was to draw a sketch, in this case free body diagram, and we also drew a cartoon, and also to choose a coordinate system that is convenient. In Unit 1, that often meant placing an object, at x equal to 0 as it begins its motion. In this case, we're choosing a coordinate system so that our job of figuring out what the net force is going to be is made as simple as possible. So what do I mean by that? Well, in order to apply Newton's second law here, I need to resolve all of these force vectors so that I can do the vector addition. And I need to make sure that I am including all in one direction and then all in another direction. This can be treated as a two-dimensional problem, but I'm going to make my job easier if I define my coordinate system in a slightly less conventional way. And that is where I have the positive x direction, I have the whole x-axis oriented along the slope, and the positive x direction pointing up the slope. And then the y direction, which we're used to thinking of as vertical, is going to be normal or perpendicular to that surface. Okay, why is this advantageous? Well, when I align my coordinate system this way, I can see that 3 out of these 4 vectors will naturally align themselves along one of these axes, and then I will not need to resolve these vectors into their components. I will just be able to say, well, when I'm summing the forces in the x direction, I've got this vector and that vector, and then whatever component of this vector I have. But it's these two I don't need to resolve anything for. And then when I do my y direction, this one just gets added in without having to figure out any sort of components. If I had chosen instead a traditionally oriented coordinate system where x was vertical and x was horizontal and y was vertical, consider that for a moment. Let's say that I had chosen this coordinate system instead. I'm perfectly free to do that if I would like. There's nothing wrong with doing it this way. But when I do it this way, notice now that only one of the 4 vectors naturally aligns along one of these axes, which means that this kind of coordinate system would require me to resolve this vector and this vector and this vector into x and y components so that I can, when I perform my sum in Newton's second law and I add up all of the forces that are acting in the x direction and set them equal to mass times acceleration in the x direction, I'm going to have to resolve each one of these into components in order to do that. Okay, so there's nothing wrong, like I said, with doing that. It's just going to make your life a little bit more complicated and tedious. So typically when you run into a problem like this where you have what we call an inclined plane, you want to try and choose a coordinate system that makes your life a little simpler. And so this tilted coordinate system is usually what we use. Okay, so within this tilted coordinate system, let's take a look. Again, we still have two dimensions to consider, so let's take a look at what's happening in the y direction first. So if I sum all of my forces in the y direction, applying Newton's second law, and set that equal to mass times acceleration, remember that the truck is moving at a constant speed, so my acceleration is going to be equal to 0. So this right-hand side vanishes, and then when I add in all of my sums, I add in the normal force and then some component of the weight force, because my coordinate system is pointing like this, right? So one thing that students often struggle with is trying to figure out how to resolve this weight vector into components with this tilted coordinate system. It really shouldn't be a struggle, but we are so used to the traditional coordinate system and the way of doing things where cosine in our mind is associated with an x component. And so how are we suddenly using cosine to indicate a y component? Well, it's because our theta, in this case, you have to think about what's happening with theta. So here, if we draw the inclined plane like this, right, then our theta is this angle here, 20 degrees. Okay, so you can do some geometrical arguments to figure out where that theta is for with respect to this y-axis here, or you can do what I often fall back on, which is to think about what happens in the limiting case. What's going to happen if I were suddenly no longer on, so the answer, by the way, is that this is going to be my 20 degrees, and so that's why we need cosine, because we're talking about the component that is adjacent to that angle. So this is the weight component in the y direction, and this is the weight component in the x direction. And that leads me to my limiting case argument. When do we ever have a weight component in the x direction? Well, we're only going to have this with the situation where you've tilted the coordinate system. In a traditionally oriented coordinate system, you could imagine just fixing this coordinate system to your inclined plane and then bringing the inclined plane down to an angle of 0 degrees. Then you want this x component to vanish in that case, right? We don't expect the weight to be going in some sort of horizontal direction when this theta were to equal to 0. And the only way that the x component is going to vanish in that case is if it's the weight component times, or the weight vector times sine of theta, sine of 0 being 0. Okay, and then hopefully you can also think about the geometry here and see how this works out to be equal to your theta right here. Okay, so although it's counterintuitive, once you sort of get it and you're used to working with this inclined plane and tilted coordinate system type of problem, then you can remember that the y component, counterintuitively perhaps, is where you resolve the weight according to w cosine of theta. All right, so I've included those two forces. They are the only forces in this free body diagram that have either some force or some component of the force in the y direction. So I have completed my sum. And in the right hand side of the equation, we have reasoned that this is equal to 0 since we don't have any acceleration. This allows me now to solve for the normal force like you see here. Okay, this has not told me anything about the tension yet. Remember, we're looking for the tension. So how can we get at that? Well, we have another dimension to consider. So let's look at what's happening in the x direction. I can do the same thing of applying Newton's second law, summing up my forces in the x direction and setting them equal to mass times acceleration. This thing is not accelerating in that direction either, so that side of the equation also vanishes. Then I need to make sure that I add into my sum on the left-hand side all the forces and or components of forces that are acting in the x direction. As we argued before, these two forces are totally in the x direction, so I don't need to do any resolution of them. All I need to do is remember to include the correct sign, just like I included a negative sign here for the weight since it's acting in the negative y direction. I need to include a negative sign here for the tension since it's pointing in the negative x direction, and also a negative sign here for the x component of the weight, which now will be multiplied, the magnitude of the weight will be multiplied by sine of theta, for the reasons that we discussed. Okay, so if I simplify this equation, now I have a second equation. Okay, this equation, now if I solve it for tension, I can now plug in what I know the weight force to be, the frictional force to be, in this case, mu times the normal force. And since I've already solved for the normal force in this first equation, I can now plug it in here. So just as I was saying with the Atwood's machine, I didn't know the normal force going in, so I couldn't have necessarily directly put that in there, even though I was given the frictional coefficient. But I've got two equations, two unknowns. This is enough to solve this system of equations. So now I have what I need in order to compute what the tension force is equal to. Whoops, let me go back. And you can see here that it works out to be 16,800 newtons. So if we work out what that is in pounds, this turns out to be sufficient for this kind of cord. Okay, so the second part to this problem is what's happening with the car. Now we're going to assume that friction is not important and we can ignore it for now. And so we're going to draw a free body diagram of the car. What we want to know is what's the most massive car we can hope to pull, in which case this tension is not going to fail us. So if I draw a free body diagram of the from the car's perspective of this object, I've got a similar situation where I've got the tension. This time it's pointing up the hill because it's attached behind the truck, and I've got the normal force and the weight force. I just don't have the friction now because I said we're going to ignore it. I'm still going to use the tilted coordinate system though, because still 2 out of 3 of the forces will align themselves along the axes for this kind of coordinate system. And this turns out to be a simpler problem because we already know what the tension force is equal to, so it's going to turn out to be the case that we only need one equation here in order to solve for what we're looking for. So if we apply Newton's second law to the x direction, again the x direction is along the incline. If I sum my forces in the x direction, set them equal to mass times acceleration, where acceleration is equal to 0, I get a similar equation to what I had in part 1. But now I've got to make sure I put the mass of the car in here instead. I know the tension force this time, so I'm solving for something different. This time I'm solving for the mass to see what kind of mass this sort of tension will be able to handle. And so when I do that, I find that a value of 1880 kilograms, which should work for just about any car you're going to encounter. So that's a rather complicated example. These inclined plane problems tend to be rather challenging for students. So if you want to take the time to go back and pause the video, go back and re-listen to some parts of it, I'd encourage you to do that. As I said before, I also have this worked out on the whiteboard in a separate video, so go ahead and check that out as well. And next time we'll do some more examples.